All right. Well, hey, everybody. Thank you so much for coming to our AI 102 panel. I am Blair Hanley Frank. I'm a writer for VentureBeat. I cover cloud and AI. I am here with an absolutely fantastic panel of wonderful, smart people who will be helping us learn some more about implementing machine learning in your company and sort of how to deal with the myriad universe of approaches out there. So if we could just get started by having my panelists introduce themselves and what they do at their companies, that would be great.
Sure. Erbil Karaman. I'm the head of product for Lyft's marketplace team, which powers almost all of our AI data science platforms, including our dispatch system, matching systems, pricing systems, including the autonomous platform that we just announced. We'll be powering a transportation network that will enable any autonomous provider to plug and play. So that's what I do.
Anthony Goldbloom. I started a company called Kaggle that we're now part of Google, and we're part of Google Cloud, but I still run Kaggle, but just now inside Google.
And I'm Joe Bentley. I run software engineering for GoPro.
Awesome. So I'd love to get started with how are each of you using AI and machine learning with your work, and how does that inform what your company does? Joe, let's start with you.
Megan, my partner in product, just did a little presentation a few minutes ago about quick stories. And that's probably the most compelling way that we use machine learning or AI. And so one of the things that we have, people go out and they film their passions with our cameras, and that might be skiing or snowboarding or just kids and pets and family. And the challenge is that when you strap a camera to your board or to your bike or to your helmet for a couple hours and you're in that moment, you end up with all this footage afterwards, and you end up like 2 hours of footage, and how do you find the sea turtles? And so we want to make it really easy for customers to find those really special moments and then build a video that's really short and to the point, and then share that. And the challenge that we have is how to find those moments. And so this is beyond just image classification. It's moment identification. It's like an activity. Where was the jump on the mountain bike, or the jump on the ski, or when did your daughters come into the face of the camera, or where was that sea turtle? That's the moment that you want to share on Facebook or Instagram. And so we're using algorithms, starting simple algorithms from just signal processing, but also using support vector machines to find, using the telemetry and so forth, to find these moments and then automatically generate stories for customers. So that's the core of what we're doing today.
So Kaggle itself probably does less machine learning than both GoPro and Lyft. We're more of an intermediary. So what we do, or what we're best known for, is companies will bring a problem to our website, we put it up, and any data scientist or machine learner can download the data and compete to build the best algorithm. So to give you an example, a lot of our early work was in the insurance industry, so taking data sets on insurance claims, for instance, and trying to predict when a car was, who was most likely to have an accident, and using those algorithms to better price insurance. So what we would do is we'd take that problem from the insurance company, and we would see if, by outsourcing it to our crowd, you could get a significantly better algorithm. More recently on Kaggle, I'd say the nature of problems has shifted to more, video, image, speech recognition as a result of the arrival of deep learning and deep neural networks. So that's where a lot of the activity is now in machine learning, and so the composition of Kaggle problems has really shifted from structured data to, more of the image recognition, speech recognition type problems.
It's probably fair to say that Lyft wouldn't be Lyft today if machine learning wasn't a big part of it. Almost everything we do today is driven by some form of machine learning and AI systems. It starts with our growth. So when I joined Lyft about 10 months ago as an advisor, first thing we have built was a machine learning platform to do better bidding on marketing systems. So you know, a lot of the different marketing solutions provide you different interfaces for bidding. You can actually do much better than them and their interfaces if you know how to bid, utilizing your own internal data as well. And that's enabled us to grow 2x or 3x faster than we were growing before. And now we realize actually we can use machine learning to predict who is most likely to take their first ride. And if they're not necessarily very likely, what kind of coupons and promotions to give them to make them much more likely to take their first ride. And then we introduce machine learning, you know, at the second step. And then we realized you can't stop there. You need to understand what are the different types of use cases and what are the different types of rides these people want to take. So you kind of like plan for different types of coupons and different kind of promotions for them. And then you realize as your system grows, it's getting harder and harder for you to predict where the demand is going to come from. It's harder to predict, you know, how to make sure the drivers are actually waiting for those passengers nearby places. And you understand that this network effect and this graph is moving so fast and it's so fluid that unless you have some of the best machine learning AI platforms, you will not provide the best service. So today where we came is almost 90% of our systems are powered by machine learning and AI. And going forward, we're expecting more and more of that to happen in the places we haven't even touched.
So that's really impressive. I think just in light of those numbers, one of the things I'm curious to hear about from all of you is for companies that may not be as far along on the machine learning journey, or even for those that are just, you know, for people who are thinking, oh gosh, I hear so much about machine learning. I hear so much about deep learning. How could this help my business? One of the things I'm curious about is this the answer to all of our problems? Is this something where everybody should just be trying to throw machine learning at all of their problems right off the bat?
Not if you don't have any data. So machine learning is not magic. If you don't have, particularly techniques like deep neural networks are incredibly data heavy, and so in order you need to have a significant volume of labeled data in order for machine learning to be useful. So maybe just to back up a little bit, there are a bunch of different branches of machine learning, and the one that is pragmatically useful and used in sort of 99% of actually useful cases is supervised machine learning. And in order to train a supervised machine learning algorithm, you need a lot of data and you need labels for that data. And so and actually, if you look at all the decisions a company makes, it's only a small proportion that fit into that criteria.
Yeah, and to that extent, there are a lot of different branches of machine learning. If you're a company with a lot of data, and if you're not utilizing machine learning or AI, you're missing the boat. That's for sure. Even if we have limited data, I've seen a lot of companies overlook the promise of some very simple methods like logistic regression, right? Even if we have limited data, there are still things you can do with very simple methods that doesn't require tons of data that might help you gain some form of efficiency, do some kind of optimization. But I agree that if you have large-scale data, if you're not doing machine learning AI at scale, you will get out-competed, you will get disrupted at some point.
So I actually found this conference to be a little bit curious because it was MobileBeat with talks on machine learning and AI, and one of the challenges that we faced at GoPro was, I agree with both these guys about data in the cloud, and when you've got particularly structured data in the cloud, that makes a ton of sense, and when you have the opportunity to communicate with the cloud, that's great. But it's we've struggled a bit because not all of our customers had connectivity to the cloud. When you're out filming sea turtles or on a mountain bike ride or skiing, there isn't connectivity. And so how do you take the data and process it all locally? And it was only like last month, I think, Blair, you wrote an article about Google putting out models that run on light, TensorFlow Lite. Which is like super exciting, and we're seeing like a lot of new processors come out with CNN capability, which is getting us really giddy and excited. But for us, it's been really a struggle to, like, how much machine learning could we bring just and run it locally on mobile? And so it was like, for us, we really couldn't get into deep learning yet on locally. I mean, deep learning in the cloud, knock yourself out. That's easy. And the frameworks for that today are amazing and awesome. But I think we're just mobile with machine learning is a really new field. I mean, like, it feels to me like only like 2 months old. Because I mean, it's like we're going like old school, like the most simplest form of machine learning still on in mobile today.
We have a very similar problem when it comes to autonomous vehicles. How do you? It's a remote mobile device, you know, in a sense that how do you enable local computation? Because you want to use the battery for driving, and you don't necessarily have connectivity at all times, so you can't communicate with the cloud at all times if you're in a remote area. And we are looking into 3 different things happening. One is, I think there's a lot of unique chip design and chip architectures coming up that are going to make local computation more feasible. And we're seeing, you know, TensorFlow Lite type of stuff where actually you can do certain type of computation locally as well. But even with that, we feel like we need to invent a form of knowledge transfer to these like lighter machines that they can take and do something with it, even though they don't still run the deep learning models. And once they collect enough information and do everything they can locally, the problems they can solve, they can transfer back to the cloud as problems they couldn't solve, and say, you know, here are the problems I couldn't solve. Please solve it for me. Let me know what you learned. Let me know how I can deal with them going forward. So it's a very similar problem on the autonomous vehicle side, and there's going to be probably multiple different approaches to solve them.
So, Joe, I mean, just to make this a little bit more concrete here, one of the things I'm curious about is how is GoPro addressing that issue of sort of reduced computational capabilities on mobile? What are you doing right now to enable that sort of intelligent experience without necessarily leveraging massive amounts of deep learning compute?
Yeah, so it really comes down to when you look at solving a problem, it is, I think you were, at least when we were talking earlier about, you know, is everything solved with machine learning or deep learning? A lot of times when you solve it, you can use really simple signal processing. And an example is our cameras today have gyroscopes and accelerometers. And so for us, we were thinking like, what's a jump, or what's interesting on a mountain bike or a snowboard, and it's hang time. And so it's when you're approaching 0 Gs there. And as we looked at the graphs of that, it's really easy actually to measure hang time, and we can do that with signal processing. As we got into it, if you look at our mobile app today, we wanted to do interesting things like people love taking pictures of sunsets and horizons. And as we got into that was more, that did require machine learning, but it wasn't, putting image classifiers on there was also not something really easy that we could do. So that was done with a random forest algorithm. And, it's just really looking at, horizontally scrolling down and looking for a line in the image, and then training that with a relatively simple, lightweight machine learning algorithm. So for now, every time we look at this problem, it's really, we're trying to look at the capability of the mobile device, the memory, the CPU capability of that, and what can fit. And is there a lighter, more performant way of doing that? I am interested in learning what you guys are doing at Lyft, which is like, is there augmentation that you could do with with the cloud, which is like, once you do connect back to the network, can you upload some data back up and bring that down? And that's what we see a lot of companies doing. We're looking at ways to do that as well. Anyway, I hope that.
Yeah, no.
Just going to add that I think this is an area where Google has invested a lot. So it's not an area that I work on, but more as a consumer, you notice that sometimes when you use the voice assistant or use WordLens or use one of those Google products, they will attempt a TF Lite model on the phone, and then if if the model on the phone is not sufficient to give an answer with a high enough level of accuracy, then it gets kicked off to the cloud, which obviously is difficult in your situation because you don't always have the option of connectivity, whereas they do. But that's a model that works when you have the option of connectivity.
So one of the interesting things about data science and machine learning and how to marry it with existing products is how you make the two cultures coexist, and how you take sort of a very experimentation-heavy field with a sort of traditional engineering structure. And I'm curious to hear what are the ways that you've seen that make that successful? And what strategies do you have to help other companies along that path?
I'm happy to have a first go. I think there's a really big difference in mindset between somebody who is a machine learning person and someone who's a software engineer, and it's often doesn't translate very well. You take a very good software engineer and try and turn them into a machine learner, and often there's a bit of organ rejection. So one of the things that a software engineer is used to a situation where there's a bug and you can deterministically go and chase down the bug. When a machine learning model performs in a strange way, it could be that there's a bug, or it could be that it's finding an effect that you didn't expect, and there is not always, it's not as cut and dry to go back and debug a machine learning system as it is a software engineering system, and so a lot of the best software engineers struggle with that. On the flip side, as you say, machine learning is really, there's a lot of experimentation, depending on if you're training a model like a gradient boosting machine, which does very well in Kaggle competitions, the thing you've got to do is trial and error lots of different features, right? Most of them won't work, but you've got to keep trying and trying and trying until you find a feature that works, and it's real trial and error. Or similarly, if you're training a deep neural network, the thing that matters is the architecture of the network. And so again, there's a lot of experimentation to come to the right architecture. And that comes naturally to somebody who has more of a, maybe a science mindset or a statistical mindset, where hypothesis generation is a big thing, and not so much I'm trying to get from here to here, and I'm trying to get there in the most efficient way. So it's just a difference in the temperament of the person who will do well in each.
Yeah, I would say, to add to that, now that actually we have more than just data science, engineering, and machine learning, we have data scientists, data engineers, machine learning scientists, machine learning platform architects, machine learning product managers, decision scientists, economists. So the list goes on, and the reason behind some of the classifications and how they kind of like work together goes back to the point of some areas you need to be able to feature engineer, you need to be able to hypothesis driven and understand why things are happening. And some areas you just can't approach that way. If you have a deep learning system that you want to optimize, you just can't understand what's going on in every single step of the way and which features are impacting what. So debuggability and observability of certain systems, as it goes down, engineers will hate it, right? Because they will get the bug reports and they will be like, what happened? And then they will have no way to actually go back and say, okay, this is the reason why it happened. They only have like this black box to blame. So this is actually how some people call it. They call the deep learning platforms, we have black boxes because you can't go in and debug it, right? So it's really hard in terms of like, where do you start building these platforms where observability is actually less important than achieving the objection, achieving the optimization, achieving where you want to get to, and where do you want to keep observability high enough so actually you can have an efficient discussion and hypothesis-driven decision-making. So, and by trying to optimize for that, we came to the point of like having all these different distinctions where we're not trying to marry everybody, we're trying to marry the right groups with each other.
Yeah, for us it was really just optimization a bit, and so we kind of had to blend a certain number of engineers sitting with our particularly our machine learning team, and it was, so some of them have signal processing background, others just have optimization on platforms is for us, we're trying to get a lot of our algorithms to go across from the cloud to mobile to other devices as well. When you look at models, if you load them up with floats versus ints or something like that, how can you compress these down to run on smaller and smaller devices? And the tradition, in my experience, our teams were the ones that were great at optimization were more the engineers versus the scientists. Could write great Python code and build complex models, but couldn't get it compressed quite down. That's where we had to have the teams help each other out. So.
Yeah, I mean, that's one of the things. I end up talking to a lot of data scientists, and one of the things that they say is that this is one of the key things that people run into, is that there is a difference in procedure and a difference in approach. And so it's interesting to me to try and figure out what the best way to navigate that is. And one of the things that's really fascinating to me about what all of you have said is that you've illuminated sort of several different approaches, everything from creating a gradient of many titles to let's find the right people to work together, and on a particular problem. And so one of the, speaking of those differences between machine learning and engineering, I'm also curious to get a sense of, as companies are starting down this journey and they're starting to kick the tires, they're starting to experiment, what are some of the non-obvious pitfalls that people may not expect to see and yet pop up frequently?
So probably the biggest pitfall that we have exposure to on Kaggle is overfitting. So just for context, overfitting is when you train a model and the model does really well on your training set, and then you go and put it into production, and then it's useless. So what you've done is you've found patterns that are very specific to the data set you're training on that don't generalize. And that happens a lot. And just a little bit of nuance around how we see this and why this is probably the most common pitfall I'm aware of is we run machine learning competitions. We give people a training data set, then they upload their models, then we score them on a test set that they never see, right? And so what happens is people will submit their models, and actually what we do is we give people a live leaderboard on a small sample of the test set, and then we throw that away and rescore them on a second test data set. And what we find is people who are new to Kaggle, new to machine learning competitions, will do really well on the public leaderboard, then we'll throw that data away and we'll rescore them on a new test data set or a new data set, and the model performance just sinks. These are often people who have good jobs at good companies, well credentialed, but when they're working on their jobs and the test data is not locked away, there's nothing preventing them from overfitting, and so they develop the habit of using techniques that end up overfitting. And so I think it worries me a lot that a huge proportion of the world's machine learning models that are in production or that are making up research papers that we all read are actually overfit models. So that's my biggest pitfall.
To add to that, there are two types of companies. They will always have problem adopting machine learning initially. One of these companies are the ones who do a lot of stuff by A/B testing, changes live, and they will run into challenges with how do you A/B test a model against another model in a live system that you only build offline, right? Especially because a lot of people started offline model building. How do you really experiment with models? And it's going to get worse if you care about a large spectrum of outcomes, right? Like you're not interested in average, you're not interested in mean, you're interested in the whole distribution of outcomes. How do you really understand how this model does better than the previous model on all of these different ranges of spectrum? And when it doesn't do what you want it to do, and if you don't necessarily have enough data to really understand how it does in the spectrum, how do you really make these decisions? And what ends up happening if you don't have the means to make those decisions well and evaluate models well, you end up trusting your offline evaluation, which ends up taking you to somewhere that you don't know where. And we struggle with this a lot, and we're still struggling with this a lot because as we grow our data science and machine learning teams, it's just we're hitting the limits of how many live experiments we can run and how many live models we can run to compare. Even at our scale, the data we're getting is not enough to read really into the models to understand what's performing, what's not performing. And we expect this to be a continuous challenge going forward too.
Yeah, we actually used A/B testing as well, and it's one of the only ways that we can really validate. We also have internal betas and conversations and debates and whether it's good enough or not. And I still vividly remember some of those conversations. But it is, it's definitely, for us, it was the only way to really drive out the pitfalls of this. So I had another point, but I'll come back to that.
Yeah, well, and it's, I will also add in something that I heard recently, which is that machine learning systems fail in ways that are unexpected to humans. And so that's one of the things that always kind of surprises me, is that because these systems don't always think in the same way, air quotes, in the same way that we do, you can end up with interesting and bizarre outcomes. I remember I've heard a story of one team that was trying to distinguish between dogs and wolves, and a particular kind of dog and wolves. And it's, that's a pretty known computer vision problem. You have one set of dog images, you have one set of wolf images. You build a classifier to distinguish between the two, boom, you're done, great, right? Well, it turns out that all of the wolves in their training data set had snow in the background. And what they had built was a very, very advanced snow classifier, because that's what the system ended up looking for. And so, and that same sort of issue around feature engineering also comes up with, classifiers that are trained on popular data sets. One of my other favorite heuristics is if you want to see if a machine learning system has just been trained on ImageNet, feed it a picture of a human. Because ImageNet doesn't have a category for human, it will often identify it as seatbelt. Because when you're trying to identify a seatbelt, a lot of humans are wearing seatbelts in those photos. So there are interesting and funky pitfalls that abound in this world. So with that in mind, what are some good strategies for actually going in and starting to test when you're working from ground zero? When you're like, all right, I've got my data, I'm ready to go, I'm really sure that this machine learning thing is right for me. How, you are there, the world is your oyster, you have all the compute you could possibly want. Where do you begin?
This is a very good question, and reminds me a lot of the late night emails I deal with. So our CEO, Logan Green, he cares about every single experience so much that whenever he sees something that he thinks Lyft could do better, I'm one of the people he sends the email to and says, why is this car so far away and the prime time is high that I can't even get? It's just like the moment I get an email, it's a nightmare because I want to do something about it, I want to understand, but there are 15 chained models that drive that live experience, right? There are 15 chained models that does ETA predictions, routing predictions, matching algorithms, dispatch algorithms, and navigation. It's just like so many chain systems that where do I even start? And I can't tell him you're an outlier, I don't care about you, you don't fit to my model. I can't tell him that. I need to go and figure out what to do. So we built systems. We call them Oracle, Godfather. We have different names for these systems that are simulators that does model evaluation, and that kind of looks at what we call as hyperparameters and some of the outcomes we care about, and tries to tell us early signals for what this model can do differently than other models. So a lot of the times we run our models first through these systems, Oracle and Godfather and other simulators. And by the way, we're going to open up some of these systems. We're just like tightening them up to open source some of them. We'll start with some academia outreach in the next coming months. And because we think these models are very, very valuable, and these systems and simulators are very valuable to understand early signals where these outliers happen and where these kind of like failures happen. And to us, that's the best way to start, and it's a very rapid way of evaluation. And then once we're confident, actually, we don't necessarily see those crazy outcomes, then we deploy them to basically our experimentation systems in live, and then we do a lot of different testing methodologies to understand really where the outliers happen. But there's no really good way. It's just we're trying to patch our ways in, and we're trying to, as we find good solutions, try to share with other people in the industry, because I feel like everybody will have these problems at some point.
I hope you're not calling the open source product Oracle.
Sure. Well, I mean, we have similar challenges as well. But I mean, this kind of reminds me of a story of the old. One of the ways that I've found to solve some of these problems is creating, you start off with the data annotating, and it's really about trying to get the right annotators. But you never have enough annotators. You never have enough data to really test the different groups. But when you can build a system that can feedback on itself and build annotation as you go, then you can get it really, really powerful. And that's one of the things we really hope to do with the problems we're working at GoPro right now. And we're working on some of those systems, and that's where engineering comes in. But as you were telling your story, it reminds me, prior to GoPro, I did Fire TV for Amazon, and we were the first to use Alexa in that. So the voice search in Fire TV was started with Alexa. And in the early days of that, similar sort of thing. We did a demo to Bezos, and I picked it up and I said, Mission Impossible, and it nailed it. And then I said, Curious Case of Benjamin Button, and I picked that because it was a long phrase, and it worked. And so he grabbed it out of my hand, and he said some Star Trek movie because he's a Star Trek fan, and it failed. And he goes, "Why is that?" And I said, "Well, we only have 1,500 samples, and it doesn't, we don't have enough samples right now. It's really trained to my voice. I'm one of the 3 people that's actually using it, and so what ended up happening was, as we spent the year building that product. We ended up having to get go out and get more data. So we had to get kids, and we had to get non-English speakers, people with various accents who English wasn't their native language. But what got us right, because this is one of the features that didn't work very well in the product. We were like worried that we were going to have to slip the date or whatever. And what it came down to is we built a feedback loop so that, every time so Jeff actually said, since your accuracy is not high enough, you need to have a disambiguation step. So if you look in that product, and you say Mission Possible, there's a menu that drops down that says like Missing Possible or Mission or whatever, and then you pick the right one. If you pick the one that the confidence score is not the highest, it records that and goes, why is that? And it puts it off to the side so we could do analysis, because the customer should have picked the 80% accuracy or higher, but when it didn't. And so really with this, to me, comes down to building in a UI and feedback UI loops into your product, because if when your customer is not picking the first confidence, it annoys the customers when you give them the wrong choice. But 2, if you get that back and analyze when you miss the confidence, and then rebuild your model, retrain the model, and if you actually, for us, we recorded all those voice searches that came in, and then we could just use that new data as examples of that. And that was, for me, that was the lesson learned out of that product. Is we're going to get this better by building that feedback loops and essentially the misses, taking all the miss off that. But.
I guess I have a little bit of a different approach, which is, and this is also the guidance we give to people who want to get started on Kaggle. Start very simple. So, I'll give you an example. We hosted a competition to predict redo the World Chess Federation's chess ratings. And so, you know, if you're starting up with that problem, start by predicting every game is a draw. So it's probably not a very good model, but it's something, right? And then it gives you something to try and improve on. So maybe you think white wins slightly more than black. I forget, there is an advantage one way or the other. So you always predict white wins, and then you get a slightly better model. And then, you know, maybe you use techniques like logistic regression, or I think random forest is probably even a better, machine learning 101 algorithm. And so at least then you sort of get a model built, get an accuracy. It's going to be pretty crappy, and then keep iterating on it until you start to approach a level where, okay, this is a model that is useful. It's more useful than my alternative ways of solving this problem. And over time, you'll starting simple and building up complexity with time is a really good way to go from zero machine learning to some models in production that are actually going to be useful.
Awesome. All right, well, we've got about 10 minutes left, and I would love to open this up to questions from the audience. So if anybody has anything, I will call on you.
Yes. So just was wondering about, like, if you could talk the scale of your training sets and models and things of that nature, just in terms of, like, you know, number of annotations, things of that, just for context.
So the question here is, he's asking about the scale of training sets and models and sort of how big the amount of annotated data being used is.
I can give you a rule of thumb, but it's incredibly dependent on what sort of data you have. So first, if somebody brings us a problem, we won't take it unless it has a minimum of 500 rows per class. So if you have if it's a binary classifier and you're trying to predict true or false, you need at least 1,000 rows. If you have 3 classes, so you're trying to predict, I don't know, take images of cars and find car color, and you have 3 car colors, then it's 1,500. That is our rule of thumb. It's a rough rule of thumb. So the things that require a larger data set is when the signals are weak. So an example is genomics data is very high dimensional and typically has sort of very subtle variations that have an impact on a phenotype. And so if you don't have many patients, you're probably not going to pick up the subtle variations very well. So, you know, the subtler, the weaker the signals in the training data, the larger the data set you will need. But I would say that 500 number is probably a rough rule of thumb as a lower bound.
So the question is, how do you go about the change management, getting from today in a company where you might not be using any machine learning into a future where you need to have machine learning at a time when machine learning is a very high strategic priority, but companies aren't necessarily doing it often for organizational reasons?
This is not just, I think, retails. A lot of tech companies actually have this challenge as well. You need to find the right type of people and then the right initial problem and team to embed them in. A lot of times when you embed them in a team that doesn't necessarily, have any interaction with machine learning, and they have already built so many operational components, which was the case when I started advising Lyft. Most of the communication platforms were built on very traditional tools with very simple logics and kind of like one-size-fits-all type of stuff. you have to like find the problem that you think where the personalization, even the simplest version of it, is going to make a huge difference in carrying the objective of the company or department. And you just like put the right person in there and just tell them, just do a few iterations on personalization and see where it takes you. And then just ask them to share the results after each step of it. And it's just immediately obvious that everybody else that that's the path forward. And then they start listening to this person you put in more and more. And then you basically find other problems for them to go and personalize further. It's just about like how do you couple those two things very well? How do you find the right person, the right initial problem? So like people don't just like, say, we tried it didn't work, move on, get out of the way. Which happens a lot, unfortunately, and we had to start from scratch maybe a bunch of times to get to a point where today almost everything is personalized because we're able to show the value.
I mean, the only thing I would add, the tools are becoming ubiquitous today, and I mean, there's so many. It's easier and easier to experiment with machine learning. It just seems to be accelerating. But like all these lessons, when you're trying to prove to make an investment in technology or an area, I think for me it's always measuring the results. Like, make a hypothesis on what you want to prove, that you can convert sales at a higher rate or whatever it might be in the case of retail, and then make sure you instrument it with analytics so that you can show the results. And the bottom line is, if it actually does, if this personalization does convert better, then you've got the data to show that. Because I think sometimes we jump in and we fail to instrument with analytics, and that way we can show the actual results. So that would be key.
I really like Joe's suggestion. One challenge, though, is that a decent number of the use cases you pick actually aren't going to work out, right? So sometimes there's signal and you can predict things really accurately, and sometimes you can't. So you want to pick that first problem pretty well and hope like hell that there's signal.
Good point.
Next question.
So I think the question, just to repeat, is, object identification, speech recognition, like those are very common problems that have been worked on when it comes to deep learning. And your question is, are there more novel or other areas where deep learning has shown progress? One thing that we have looked into a lot is what we call the structurally encoded neural networks. And what I'm trying to get to is there are problems you can translate to the problems that you're talking about, to use the system architectures that have been built for those specific problems. So one example is routing, right? So routing is a big problem for us. There's no like paper on how routing problems are solved utilizing deep learning, and there's no architecture, but you can translate the problem of routing if you have the right encoding kind of system to translate whatever input you have to vectors that can also be the inputs to the same system that does object recognition. And that's one way we found success, kind of translating different types of problems to fit in, because the challenge is you can take on novel problems and try building architectures from scratch. It's just a lot of time you need to invest into that without knowing what the outcome is going to be, especially if you automate progress. So we always try to figure out, okay, what are the good architecture and systems that are working, and what are the other different problems we can translate into this solution.
I was going to push back a little bit on the question. So there's a famous quote, I think, from one of the pioneers of artificial intelligence, John McCarthy, who said, it's called AI until it's possible, and then it's not called AI anymore. Which is that, I would say that the ability to do much more with image recognition and speech are actually remarkable fundamental breakthroughs, like really remarkable. And I think we're scratching the surface. So we started off with these things being used for frivolous use cases, like distinguishing between cats and dogs or dogs and snow, to use the example from earlier. But now we're moving on to real use cases that are really, really exciting. So just some of the use cases that Kaggle has done, where deep learning has been an enabler. So taking CT scans and diagnosing lung cancer was one from this year. Taking MRIs and diagnosing heart failure. We're doing a competition at the moment with a $1.5 million prize. You know when you go like this at the airport? At TSA. So identifying where you have a threat object on you when you go through those scans. So at the moment, the false positive rate is very high, trying to reduce that. So I would say that we have deep neural networks unlock a really valuable set of fundamental use cases that have not really made their way outside of companies like Google into production in a meaningful way. And so I think a lot of the exciting applications of deep learning, just based on those image recognitions and speech recognition use cases, facilities still to come.
All right, we've got time for one more question.
My question is, how do you prioritize which product, which features to build? And of course, because machine learning can solve multiple problems. For example, for GoPro, what was the rationale that I want to build out quick story matching, that sort of feature? I think maybe I'm sure there are some other million-dollar problems that you would like to solve, but how did you end up solving this problem?
Yeah, that question's easy because Megan Laffey's sitting right behind you, and she runs product. But in seriousness, we have, for us, we have a fundamental goal that, we know that our customers, when you're in this passionate moment, you just experienced something, you saw a sea turtle, or you did a mountain bike jump, or whatever it is, that you're more likely to share if you're in that moment, and the more time that we can collapse that time that you're in the moment to sharing, and for us, the more you're engaged with the product and sharing, and you see GoPro videos out there all the time on YouTube and Instagram and so forth, and that drives this virtuous cycle for us. And because people see other people experiencing life, and then they want to go out and have a great time as well, and then they go out and buy our cameras, and the cycle continues. But this is a constant goal for us. I mean, this cycle will never stop, and we want to reduce to the moment that the day that you can get you go out snorkeling, you jump on the boat, and the sea turtle's right there, and you can just hit share. That's magical, and we're not quite there yet, but we want to be there, and I think our problem is not dissimilar from autonomous cars or from various AR glasses where you're trying to see the world, and they can help you see what book to pick out of the bookstore, or to avoid the dog crossing the road or whatever. They're all very similar problems, and we want it in real time. And I think for the challenge for us is how do we pick that? It's part of wanting just to please the customer. It was a customer goal. We know from ourselves and using the product that when we're in that moment, we want to share how fast can we improve that, and that's why we picked that feature and drove it, and just making it super easy and synonymous. Connected to the phone there, but others?
To add to one thing that you specifically said, it's about the magic that you want to create, and the way you can create a magic that's not easy to copy is by leveraging your network and leveraging your unique data. So the way we look at how to create magic is actually always around, we really try to dig into what's really unique about our network and what's really unique about our data, or where we can create more unique data sets that we can do something about it nobody else can, and we can create magic that is very hard to copy, but it's very easy to identify and and accept for the customers. So that's kind of how we think through prioritizing some of these features.
Awesome. All right. Well, thank you all for coming. We've got some more sessions on the main stage coming up after a short break. If you can please join me in thanking our panelists.
Thanks very much.